Morning, folks. Welcome back. Hopefully, break was good for you. Today, what we've got is we're going to start in on Newton's laws and free fall. So, a couple things to be aware of. Um, Quiz 3-1 is on Thursday. Um, I'll release topics for you tomorrow on that one and Wednesday on that one. I'll also review with you on that stuff. Quiz 2 is next Monday. Lab 3-1 is going to be on Friday. I'll run you through that, show you what that thing looks like. And then your test is next Thursday. All right. Today, what we're going to do is we're going to talk Newton's laws and free fall, universal gravitation, free fall acceleration. Then I'm going to show you homework 3.1 and hopefully get you started on that sort of stuff. Okay. So here we go. All right. So Newton's first law. Probably remember this one or heard this one. Object at rest remains at rest. An object in motion continues in motion. That's probably the part that you've heard. Now, the other parts of it that we may not have heard is that an object in motion will continue in motion with constant velocity unless the object experiences an unbalanced external force. So, usually when we say an object at rest stays at rest, object in motion stays in motion, that's to the extent that people know. All right. So, when we talk about this too, the more massive an object is, the harder it is for it to start moving and speed up, slow down, stop, and also change its direction. All right. Now, if those look familiar, they should. Remember, those are accelerations for us, right? When we talk about Newton's first law, it's often referred to as the law of inertia, right? An object at rest is going to stay at rest. Why would it move unless there's an outside force, right? An object in motion is going to stay in motion unless there's an outside force, right? Now, the second part of that becomes a little bit disconcerting for us or a little bit troublesome for us because when we think about a vehicle and we're driving and we let off of that gas, right? As soon as we let off that gas, we start to slow down. Well, what happens is there's actually an external force. That's that wind pushing against us, aerodynamics, right? If we were in a completely wind-free environment, also friction on the tires. Forgot about that one almost, right? If we didn't have either of those two things, our car would continue to travel. Think about outer space, right? If you start your rockets on your thruster pack or whatever you have when you're doing a spacewalk, and all of a sudden you get too far away, well, you're going to continue on forever and ever and ever, right? Well, not a bad thing necessarily, maybe, but remember, that's probably likely, somewhere between maybe an 8 and 15-minute air supply in there. So eventually you're going to pass away, unfortunately. That's not something that we want to have happen, right? So that's why when we see spacewalks, they are so close in saying all the foreign agencies because they want to be tethered. They want to make sure that if they do end up getting too far away, that they have that tether that holds them and brings them back. Okay? Like I said, this is often called the law of inertia for us. Object at rest will stay at rest. So this leads us into a concept that we talk about as universal gravitation. Now, don't write down that formula yet. We'll talk about that formula a little later. So please don't look at that formula right now and kind of get freaked out by it. Big G m1 m2 d squared. All right. G is our universal gravitation constant. M1 and M2 are the masses of both objects, and D is the distance between the center of gravity of these objects. Now, when we look at this formula, this helps us to explain how gravitational pull happens. So, when we look at this, I just want you to understand conceptually what's taking place here. Right now, our algebra is not ready. Right now, our physics isn't ready for us to actually start to attack this equation. So, when we look at this one, right, it allows us to combine a couple things, inertia and universal gravitation. We always have, anything that has mass is going to have a certain amount of gravitational pull. Now, we may not necessarily realize that when we look at like ourselves or a pencil or a pen or something like that, but it does have gravitational pull. Now, in the grand comparison between a pencil, ourselves, the table, the chair, whatever we're looking at on the earth, it's so much less, so much insignificant, meaning that the mass of the earth is so incredibly huge that it dwarfs any mass that we can use here to talk about that. Okay? So, if we take a look at this, right, and we take a look at different massed objects at the same distance from Earth, the larger object would feel a more massive pull then. Meaning that if we looked at, say, the moon versus, a perfect clone of the moon farther away. Well, because of the distance between the moon and this new clone moon, what we're going to see is that d squared on the bottom now it really starts to cut down the gravity. So as you think about it, right? If we think about us here on the surface of the Earth versus us out even past the International Space Station, there's going to be less gravitational pull for us, right? That's why it appears like our astronauts in the International Space Station are weightless, right? You reach a certain point away from the Earth, and all of a sudden now you get this weightlessness look, right? It just means that your mass hasn't changed, the mass of the Earth hasn't changed, the universal gravitation constant hasn't changed. It's just that your distance has changed. Okay, so when we look at this would cause it to fall faster, right? Because it's more massive. So if we look at a bowling ball that is 15 pounds versus a bowling ball that's 5 pounds, right? If they're both at the exact same distance, say 10 feet off the ground, the higher mass one should experience a greater pull of gravity, right? But think about this. If we've got that 10-pound bowling ball, is it going to be easy for that to start? Think about when you're sitting at a stoplight and all of a sudden you've got, some sort of tractor trailer or, big dump truck sitting next to you, right? That thing takes a while to get started. Most of us, what we do is if we see that, that big dump truck next to us, we're going to move over to the other lane because we know we can go faster, right? It's way more difficult for that thing to get started and start to move, okay? So when we look at this, we ask the question, as our objects fall toward the Earth, why would they all fall at the same rate? Meaning that when we talk about middle school science, most middle school science teachers are going to say, well, yeah, they do fall at the exact same rate, right? Take air resistance out of it, and all of a sudden now everything falls at the same rate. But why? That becomes the big question. For us, what we have to ignore is that concept of air resistance, right? If we take a piece of paper, that's just going to float down, right? You take a parachute, it's going to float slower, right? We even take our own bodies, and all of a sudden we go as aerodynamic, like a pencil dive type thing. We're going to go really fast. We go really wide out, we're going to go a lot slower, all right? That aerodynamic piece is going to cause us to slow down. So then we ask the weird question, which would fall faster in a vacuum? Vacuum meaning that there is no air there. Think of dropping towards the moon. A feather or a coin? Well, it's somewhat of a trick question, right? Most people will say, well, the coin because it's less aerodynamic, right? Or it's more aerodynamic, sorry, whereas the feather is less aerodynamic. Well, what should happen is that they both would fall at the exact same rate. Now, which leads us to this concept of free fall. So, when we talk about free fall, we have to talk about an acceleration due to gravity. But what we talk about is this is negative 9.8 meters per second, or negative 32 feet per second, meaning that after 1 second, you should be going 9.8 meters per second. After 2 seconds, you should be going 20 meters per second. All right. So we use the symbol as g equals negative 9.8 meters per second because that gravitational pull, yes, it'll vary depending on how high off the surface of the Earth you are. Meaning, you go to Mount Everest, obviously the G is going to be a lot less because you're further away from the center. If you go to, Death Valley in California, which is the lowest, place on the surface of the Earth, it's going to be a little bit more than 9.8. But for us, the variability of that means that really, it all depends on where we are. For us, we're looking at 9.8 as being our gravitational pull here in the Great City Lake. Okay? So, we can still use these kinematics from last chapter. Now, the one thing I will warn you is that, yes, we can go ahead and change these, right? So those are our three big kinematics that we had last chapter. Our average speed equals delta V over T, Vf squared equals Vi, and so on and so forth, right? You can read those as well. But what we could do is we can do these. Now, I don't think this year we're going to push this as hard. But what I want you to understand is that all of this gravitational pull, all of this negative 9.8, we can use that anywhere you see G on this one. We can also use that in all of our previous equations wherever we see A. All right? Now, not to get too formula crazy, not to change too many formulas, but please, please, please understand that we can use free fall as a concept of the same kinematics that we just got done using. Now, a lot of our kinematics we used as horizontal, right? We talked about a car speeding up, or we talked about a car slowing down, or we talked about, running a certain distance. That was all horizontal. Now we're going to talk about throwing an object up, or we're going to talk about dropping an object down, okay? So when we look at these, yes, these become delta y's. So something that I want you to really think about is that for us, when we look at gravitational pull or gravitational acceleration, the reason why it's negative 9.8 is because gravity is pulling which way? Pulling downwards. So when it pulls downward, remember, that's not in the positive y direction, that's in the negative y direction, okay? So when we start to see like delta y in this body equation, that just means that we're either going up, positive, or we're going down, which is negative, okay? So since everything has mass, everything has a gravitational pull, which is really, really weird. Because when you think about that pencil, or that mouse, or that computer that you're sitting next to, or even that chair that you're sitting in, it has a gravitational pull. Now, is it extremely dynamic? I mean, can you feel that? No, not necessarily, right? For us, we might be able to pull up, a couple pieces of dust. Maybe we can even get some skin flakes to pull towards us, right? Because of that vast mass differential for us, we can attract a few things, not a lot of stuff, right? So everything is attracted to something else that has mass. That's a big deal. Now, is that gravitational force large? No, not necessarily, right? For us with the Earth, because the Earth is so incredibly massive, guess what? We feel that gravitational force. That's our weight, right? So when we look at how everything is attracted to each other, this becomes something dynamic for us. This means that if something has mass, it will be attracted to something else that has mass. So what you can say is that you sitting in the chair right now, your body is actually gravitationally attracted to the chair, and the chair is actually gravitationally attracted to you. Because you both have mass, there's a force of gravity between each other. Now, does that all of a sudden, overcompensate for that of the Earth? No, by no means at all, right? We can't levitate in the Earth because we have something of higher gravitational pull than the Earth, okay? So here's an example, right? 10 kilogram mass versus a 5 kilogram. We ask the question, which one is attracted to the Earth more? The 5 kilogram, right? If it doesn't say anything about distance, that 5 kilogram is going to have a higher force of gravity according to the universal gravitation formula, right? So it should be the 5 because of the force of gravity, right? How much bigger is this force? Well, the force should be 2 times bigger because the mass is 2 times bigger, right? It's not that the Earth's mass is 2 times bigger, it's that you have a 5 kilogram mass compared to the Earth. You have a 10 kilogram mass compared to the Earth, all right? So because the 10 kilogram mass is twice as big, that's where our force is twice as big. That's the gravitational force. So then we ask the same question, or we ask a little different question. Which one's harder to move? Should be the 10 kilogram one, right? Think of a heavier object, right? If you're driving a really, really heavy vehicle, it's really tough to get that thing to move, all right? When I've moved a number of different times with a full U-Haul vehicle, trying to pull away from a stop sign, and it takes forever to do, and I feel terrible doing it, right? But with my wife's Accord, and we can get up and we can go. That thing's pretty light, right? How much harder is it to move? So we have to think about inertia. This object wants to stay at rest. We have to figure out how many times bigger is that force to try and move it. So it should be twice as big, right? It's twice as massive. So, again, this is based on that concept of inertia. So, the 10 kilogram mass has twice the gravitational pull. The 10 kilogram mass also is twice as hard to move it, meaning it's going to get pulled toward the Earth twice as fast. But it may take twice as long, or it may be twice as difficult for it to get started moving. Okay? So the two results should do what? Correct, they should cancel out, proving that the 10 and the 5 are going to fall at the same rate. So now this is a whole huge convoluted way of trying to show that yes, your middle school teachers were correct. Objects do drop at the same rate. But there's a little bit more at play than just saying they drop at the same rate. There is this concept of inertia. How hard is it to start? There is this concept of gravitational force. How much pull is between these two masses? Okay? But when we look at it, this also has to negate air resistance for us. All right? Because air resistance all of a sudden starts to introduce other issues that we can look at. Okay? So different masses fall at the same rate because their gravitational attraction is exactly canceled out by their inertia. All right? So when we look at this, you take that big 10-pound mass, you take that big 5-pound mass, guess what? They're both going to fall at the same rate of speed. Okay? So, a couple graphs for you. If we drop something from rest, so to drop something from rest, how fast is it moving in motion? Should be 0. So now, is it moving forward or backwards? Remember, if we're dropping it from rest, that means that it's starting at that 0 mark, and it should be going backwards for us, right? Now, is there constant acceleration with this? Yes. Is it going to go the same speed all the way down? No, that'd be so weird. Jump out of a plane and go 10 miles an hour the whole way down. No, it doesn't work that way. You're going to speed up, speed up, speed up, speed up until you hit a concept called terminal velocity. We'll talk about later, right? So this one should just be a downward sloping line going away from the t-axis or the 0 velocity mark. Okay? We throw something straight up in the air, right? So if we throw it up, now think about that. What's going to happen to the object, right? It's going to go upwards, and then at the top is eventually going to do what? It should stop, right? And then it should start coming downwards again, right? In order to throw this upwards, do I need an initial velocity of 0? No, because an initial velocity of 0 keeps it in the palm of my hand. So I need something greater than 0, because eventually what will happen is this should stop at that apex, right? So what we see is, we see this thing starts with a high forward velocity, right? As it goes up, goes up, goes up, it eventually stops, right? The stop is the apex, right there where it crosses the line. Now it's starting to travel backwards. Remember, downwards in the y-axis is backwards. If we're going backwards, that means we have negative velocity. We're underneath the t region. That's where our area of negative velocity is. Okay? Dropping something from rest. Now, notice the difference. I got a negative y. I could have gone deep and gone negative b, right? So this one, if it's going to go backwards, it has to go downwards, right? Negative slope means backwards. So then also what we have to do is say, is this a flat or is this curved some way or other? Well, if it's curved so it plateaus, that means it's eventually stopping. So as we drop an object, does it eventually stop as it falls? No. Okay? So is it flat? Is it just a perfectly constant line? No, that means it would be falling at the exact same velocity again. This thing should be speeding up. So because it's speeding up, what we should see is this goes towards the vertical, goes towards a steep kind of drastic line down. It should accelerate as it goes downward. Okay? Throwing something straight up again, if we're looking at the delta y, remember upwards, positive, downwards is negative. In order on a delta y or a delta d graph, what we should see is there should be a stop point. At a stop point, remember, that just means it is perfectly horizontal. So what we see is it eventually climbs up, right? And what we now look at is this thing's starting to flatten out. That means it's going to stop at the top. Does it stay stationary at the top, though? Not at all, right? Gravity kicks back in and then pulls that thing back down. As it's pulling it back down from the apex, what it starts to do is it starts to speed it up again. All right? So, here's some homework for you to try out. A lot of conceptual questions here, at least in the beginning. Get your mind to think about this concept of falling objects. It's definitely very, very weird. Definitely different for a lot of people to now start to think about actually the mechanics and the physics of an object being falling downwards or also being thrown upwards. Okay. Hope you have a great Monday. We'll talk to you soon. All right. Take care. See you folks later. All right. Bye bye.